All right. Hello, everybody. Good morning and Happy New Year, or rather, good afternoon, depending on when you're watching this video. Um, for our physics class today, we are going asynchronous, so I decided that I'd pre-record a little bit of the lesson that I had planned for you, but we'll go more in detail with things tomorrow as it relates to our concepts of energy that we started before our winter break. So, I'm just going to share the screen with you and just recap a few things, and then we will get into discussion about thermal energy today. We are a little bit off of the schedule that we were following, so I will revise that for you, so there won't be any unit tests this week or anything like that. And then I will be revising a few of the assignments that are posted there as well before I go off for my maternity leave in the next 2 weeks or so. Likewise, any upcoming assignments, again, you'll see them being posted and populated on D2L in the calendar. So hopefully everyone had a great winter holiday and you took some time out for, yourself, for some self-care, relaxation, focused on your wellness, spent time with your immediate family, friends, depending on how the lockdown situation was in your area, and are ready for the new year. I don't know, depending on your circumstances or just on your own mindset, if you've made any resolutions or promises to yourself, or if you're the type of person who doesn't believe in creating a New Year's resolution, that's fine too. Maybe you're just going on with each day, one step at a time, and staying positive. So in any case, let me share the screen, and we are going to take a look back at our whiteboard in terms of some topics that we were looking at before we went off for break. So we were looking at this idea of energy, and over the holidays, you had a chance to complete your lab on student power, which incorporated gravitational potential energy as well as some kinetic energy concepts as you were going up and down the staircase. Hopefully you were able to complete that task with a partner or individually. So energy is the ability to do work, as we know, and there is a correlation between work and the change in energy known as the work-energy theorem. Energy transformations are taking place all the time, depending on the motion of an object. And those transformations, in terms of our course, we're looking at from the perspective of potential energy, or rather gravitational potential energy, and kinetic energy of moving objects. And we have the two equations here for those definitions. An extension of potential energy, or the gravitational potential energy, I should say, over here, that I did receive a couple emails about, is in regards to some ideas that we have in regards to different types of potential energy. So we have something which is known as elastic potential energy. And this is a concept related to Hooke's law for elastic materials. Now, you will actually explore Hooke's law and elastic potential energy in great detail along with momentum when you take the grade 12 physics course, so in your SPH 4U class. So I'm not going to dwell too much on this topic, but if you did go through the material that is posted online on D2L, if you are interested in solving the questions for Hooke's law, there is an equation where F is equal to K times X, and the elastic potential energy equation looks very similar to kinetic energy, where we have that the elastic potential energy is equal to half times Kx squared. where X is related to the stretch or compression of the elastic material, measured in meters, and then K is what we call the spring constant for that elastic substance. Now, the spring constant is going to change all the time, depending on the type of elastic material in the question. Similarly, if you're taking a look at the equation here for Hooke's law, sorry, everything's moving around. Remember that F is related to force. So we call this the restoring force of the spring, or an applied force to the spring, depending on the perspective or the elastic material. And then again, K and X are the same as in the elastic potential energy equation. So these are the same variables as were described over here. Now, in the case of solving different types of questions, it's pretty straightforward. You'll be given information about the forces involved and then, or the mass of the object, or a stretch or compression in meters, which is related to a distance component for that spring. Remember that with any sort of spring, it could be suspended from a ceiling or a rooftop and have a mass hanging from it. And we know that there can be both a rest position for the spring, and then once that spring gets stretched out or deformed, right, that happens when some sort of force is applied on the object as well to change its position. So we can measure this component right here in terms of the stretch or compression and how that changes over time. So that's a little bit about elastic potential energy. But for our purposes in the course, we're more so interested in the broader aspect of energy and the law of thermodynamics, specifically the first law, which states the law of conservation of energy, where energy cannot be created or destroyed, but can change in form within an isolated system, or otherwise known as a controlled environment. So what we do in these types of situations and questions is track the input of energy towards the output of energy. And then that helps us to determine both the power of the system as well as the efficiency of the system as well. And we'll talk a bit more about power and efficiency tomorrow. There are other different types of energy, as you know. There's a whole unit on waves and sound, which is coming up next. In this particular unit, just focusing specifically on energy, we will encounter thermal energy and nuclear energy sources. We'll touch a little bit on chemical energy as it relates to heat. And I've just mentioned the elastic potential energy to you. And then the final unit of the course with electricity and magnetism, you will also learn about electric energy as well. So with all of these concepts, you can speak about them in terms of theoretical perspectives. Likewise, you can also talk about energy in terms of mathematical perspective as well. So for example, if we just want to consider changes in potential energy and kinetic energy, think about holding a pen or a pencil that you have at your desk, right? When you drop a pen, potential energy is converted to kinetic energy. And we say that both of these forms of mechanical energy are defined as that which is the energy of an object based on its motion or position. Similarly, if you're standing at the bottom of a hill and you kick a ball, we know that before you initiate any sort of force on the object has potential energy. Once you set that ball in motion, it has kinetic energy because it's moving. And as it slows down and stops, the energy of motion is then transferred back to the potential energy in the ball's position. So maybe the ball is very massive and it stays at the top of the hill. If not, then it will continue moving. It could roll back down towards you or back down the hill. So therefore, there are continuous situations where potential energy is quickly being converted back to kinetic energy. So therefore, the energy of the ball gets transferred between both of these forms, so energy is conserved. Likewise, when we have more than one object in a situation, we can track the energy of both objects. We can also track the momentum of the objects as well, based upon the force being exerted over a certain amount of time as per the mass of the object as well as its speed or velocity. Now, kinetic energy can be transferred to other objects through collisions, right? So think of bumper cars, for example. You may have sat in a bumper car before, maybe at Canada's Wonderland, if you recall. So in that situation with the bumper cars, remember that when one car bumps into another, it transfers energy, causing the other car to move. So there is that transfer of energy that takes place between those objects as well. So just a little bit of theory for you to kind of wrap your minds around those situations. Now, when we're looking at the idea of thermal energy, we'll write down a brief note here, and then we'll shift into specific heat capacity as related to the gizmo experiment. I'm going to write down something here. The thermal energy concepts, what we're looking at here, is anything related to heat and temperature. And we know that temperatures can fluctuate, so we can look at this from something being hot or cold. And we'll talk about this in a moment with kinetic molecular theory. Now, for formal definition, since I know a lot of students generally like definitions, we say that thermal energy is related to vibrating molecules that affect temperature. And thermal energy is an example of kinetic energy. So it's a type of EK, right? Because we have molecules that are moving. Nuclear energy that we will look at in another lesson coming up. So we'll just define it here though, so that we have a comparison. Is related to gravitational potential energy, so it's a type of EG. And we say that it is generally energy that is stored in the nucleus of radioactive atoms. So what happens is we can study nuclear energy in the form of various reactions So we have nuclear fusion and nuclear fission. Well, nuclear fission is the process of atoms being split and then energy being released, and that's the way we produce electricity from a nuclear power plant. And then we also have radioactive decay. And these types of reactions are what we call the alpha, beta, and gamma reactions. And we'll talk a little bit more about these and how they relate as well to some aspects of chemistry and chemical energy, where energy that's being stored in chemical bonds can be broken, and we can see how different reactions take place. Now, the main idea with this kinetic molecular theory is in how particles are moving. The particles will move faster in a hot substance and move slower in a cold substance. Likewise, with the kinetic molecular theory, we can also study the behavior of particles based on their physical state. So we've got our physical states of solid, liquid, and gas. And depending on the physical state of the substance, whether you increase the temperature or decrease the temperature, particles will move in such a way as per their design or their chemical or physical makeup. So we know that something that's compacted into a solid doesn't have much room to move around, so therefore the particles wouldn't be traveling as fast. Liquids are found in the middle. We know that a liquid will take the shape of any object it's poured into, right? So they do not have a definite shape and volume. It's based off of the container or the surroundings. And for a gas, these are the molecules that are particularly spread out quite well. And we can track how an increase or a decrease in temperature will affect the motion of the object as well. So what is the actual definition of temperature then? So we say, in terms of our definition of temperature, that temperature is the average kinetic energy of the molecules in a substance. So if you, for example, want to compare, if we have a cup of hot chocolate versus a glass of chocolate milk that's from the refrigerator, right? You can compare the molecules in each one of these. What you're going to notice is that in the hot chocolate, right, this one is at a higher temperature, it's hot. We have increase in the motion of particles. This might be familiar if you've already taken chemistry. So therefore the molecules would be zipping around much faster, right? In the case of the chocolate milk that comes from the fridge, it would be at a lower temperature or somewhat cold. And there would be a decrease in the motion of particles for this liquid. So that's the difference in the kinetic energy that these molecules have microscopically. And remember that molecules can move around and they can bump into each other. So the molecules in this situation, when we think about thermal energy, are the objects that are in motion. Okay, so that's what our focus is. So before we were looking at larger objects like cars and vehicles and people traveling, moving a box up and down an inclined surface, things like that. Now our focus is on molecules. And remember that the molecules in either a liquid, solid, or vapor or gas are always in motion, which is a little bit harder to see in a solid. Therefore, when we think about thermal energy, we're thinking about the sum of the kinetic and potential energies of all molecules in a substance. So we'll add that definition here. Now, in terms of measuring temperature, as you're going through the textbook, our units for temperature are in Celsius and Kelvin. The Kelvin scale is the SI unit for temperature. So I'll note that down for you as well, under temperature. Based off of absolute zero, capital K. And then the common unit or equivalent unit, we use degrees Celsius. There's also Fahrenheit that you may have come across. And if you are not using the metric scale, you can convert between Celsius and Fahrenheit using these formulas right here. So if you have the temperature in degrees Fahrenheit, or you need it, sorry, in degrees Fahrenheit, you're going to take the Celsius temperature, multiplied by 9/5 plus 32. And if you're going the opposite way, take the temperature in Fahrenheit, multiply by 5/9, and subtract out the 32. Okay, so this one is when you are given Celsius to get it into Fahrenheit, and this one is if you are given Fahrenheit, and then you have to get your answer into Celsius. With the Kelvin scale and the Celsius scale, if you've learned your gas laws already in chemistry, then you might already know how to do this Celsius and Kelvin conversion. But if you do need to get your temperature into kelvins, what you want to do is take the degrees Celsius temperature and add 273.15, I believe, or we'll just say 273 to it. Or if you want to go the opposite direction, you're going to take the temperature in kelvins and subtract 273, so that way you're working with the correct quantity. Okay? Now, when we think about the word heat, and then we'll get to specific heat capacity, right? Remember that heat is the transfer of thermal energy from warmer to cooler. Therefore, you may have experienced this on a cold day, like the current weather we have. But when we feel that something is hot, it's because the object is warmer than our hand, right? Likewise, if we feel cold, we start to rub our fingers or our hands together to generate heat, therefore to make us feel warmer and to increase the temperature. In terms of thermal heat transfer, remember that with this transfer of thermal energy, that can be done in a variety of ways. You might remember this back maybe from grade 8 or grade 9 or something, in terms of these three terms. So conduction, radiation, and convection. So know the differences between all three of these. And that brings us to the concept of specific heat capacity. So specific heat capacity and calorimetry are the primary focus of the Gizmo experiment. As you know, if you took a look at it over the winter holidays. Likewise, I did extend the due date until tomorrow, but I can extend it one more day till Wednesday. So that way you have enough time to gather your bearings and catch up. So I'll change the date online. So that way you understand the concept. So what I'll do is right now is share with you a little bit about the equation for specific heat capacity, and then I'll point you in the direction of some other resources that you can use to study these concepts as well for this afternoon. So I'm just going to consolidate myself here. And bring up our definition. Right, the definition being the equation for specific heat capacity as related to the principle of heat exchange. So specific heat capacity is a concept that is defined as a measure of the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Now, specific heat capacity is actually a variable. So it's the variable C. So I'm just going to share with you a video on specific heat capacity. And that way it'll give you some context as well.
Hey, it's Professor.
Let me just make sure that the sound is on.
Dave, let's talk about calorimetry. He knows a lot about the science stuff. Professor Dave explains. Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension.
So this is a typical question that you would encounter if you are studying specific heat capacity in more detail, as well as going through the Gizmo lab online and experimenting with different types of materials and metals at various temperatures. So when you are looking at heat exchange, remember that when heat is transferred from one body or one object to another, the amount of heat that's lost by that particular object will be equal to the amount of heat gained by the other. That's what they're talking about in terms of the Q that's being absorbed versus the Q that's being released. And with these various substances, specific heat capacity of common substances are reported in data tables for you in units of joules per kilogram times degrees Celsius. So therefore, you wouldn't have to memorize these values all the time. They could already be given in the question. Otherwise, you'll have enough information in the question, as what we can see here in this example, to solve for the specific heat of the metal and then identify what that unknown metal might be. So keep that in mind when you are going through your Gizmo application, right? Because in this situation here, you have 4.82 grams of an unknown metal, right? Watch your units. If you have grams, you have to convert to kilograms first so that your specific heat capacity units match what you are calculating, right? You have your temperatures so far in degrees Celsius, that's good. They tell you some information that the metal is placed into water and what the volume is. It heats up to a certain amount, and then you're solving for specific heat. Right, so here we can see that the quantity of heat that's being absorbed is equal to the quantity of heat that's being released when the metal is placed into the water, and when we compare both of those substances. And if we plug in all the information into the equation here, using grams is okay because the specific heat quantity, or C or S, as in this video they're using S, is 4.186 for water. So therefore, multiplying that in, solving for the metal, we get that the specific heat capacity is 2.19 joules per gram times degrees Celsius. So I will post up some more examples for you so that way you can see how thermal energy works as well as specific heat capacity, and then use that in your review of the material for the visual lab that will be due later this week. Don't forget about your movie project checkpoints that are coming up shortly to be due with your partner or your group. And if you have any other outstanding work, please make sure that you get everything done in a timely manner. More feedback is coming your way throughout the week and in the next 2 weeks or so before I hand you over to the main team. So enjoy your day, and I will see you online tomorrow morning for a more longer session on some of these.